Alright, here are our perfect problem 1 solutions. In this problem we're given these huge numbers, 23,760 and 32,076, and asked to do a few different things with them. I think it'll be, well, I know it will be helpful to know those prime factorizations. So maybe before I go any further, I'll just figure out what those prime factorizations are. You got lots of options on how you break these down, but when something ends with a 0, I like to take out the 10 first and get to here. And then 2376, it's divisible by a lot of different things. Maybe the easiest one to see is that it's even, so it's 2 times something. And either long division or with the help of a calculator, you can see it's 2 times 1188. And then 1188 is still even, so we can take out a 2. It turns out that it's 594. Still even, we can take out another 2. 2 and 297. Alright, we're kind of running out of options here. See, 297 is not divisible by 2, it's not divisible by 5. We can check if it's divisible by 3. The divisibility by 3 check is to add these digits up. 2 plus 9 plus 7, you get 18. And 18 is divisible by 3. So 297 has to be divisible by 3. And if you do 297 divided by 3, either in your head or in a calculator or long division, you get 3 times 99. 99 also divisible by 3, or if you get really clever, you notice it's divisible by 9. So again, lots of different ways to write this, but one way or another, your prime factorization should be 2, 2, 2. So what do we got? 1, 2, 3, 4 2s. And 1, 2, 3 3s. And it looks like 1, 5. And 1, 11. Needless to say, I would never give you something this nasty on a test or a quiz. But for a perfect problem, when you can take it home and use a calculator, I guess it's not quite as bad. So okay, now we got to do that again. I'm a little short on room, but maybe I can squeeze it in here for the other one, 32,076. See, kind of same idea. 32,076 is even, so we can write it as 2 times, and then with the calculator maybe you'll find 16,038. Still even. Oops, 8019. No longer even, but if you sum up these digits you'll see that it's divisible by 3. In fact, it's divisible by 9, but I'll do it this way instead. Sum up these digits, you'll see it's still divisible by 3. Still got pretty big numbers here, but we're starting to get a little bit smaller. 891, sum up the digits, still divisible by 3. What is that, 297? Oh, we've seen 297 before. So you can keep going with this tree, or you can kind of, let's see, how should I write this? 297 is 3 times 3 times, well, I'm going to copy the tree above. I'm not going to try to cut out any steps. 297 was 3 times 99, and 99 was 9 times 11, and 9 is 3 times 3. So I barely can fit in that this is 2 times 2 times 1, 2, 3, 4, 5, 6 3s. And finally 111. Wow, what a mess. So that's a lot of work, but it turns out we're almost done, even though we haven't done anything. We have the prime factorizations, which will help us do all these problems. So this first one, I should probably change color so things don't run into each other. Instead of 23,760, let's think about it as 2 times 2 times 2 times 2, 3 times 3 times 3, 5 and 11. That is, think about it as this prime factorization here. And then divide that by this prime factorization. 2 times 2 times, what did we have? 6 3s? 1, 2, 3, 4, yep. 1, 2, 3, 4, 5, 6. And then an 11. And what we can do is cancel out a lot of stuff. This is the kind of satisfying part. These 2's cancel. These 2's cancel. Those 3's will cancel. Those 3's will cancel. Those 3's will cancel. And that 11 will cancel. So what we're left with, looks like we have 2 2's up top. and a 5. And on the bottom we have 3 3's. And if you multiply those across, you get 2 times 2 is 4, times 5 is 20, 3 times 3 is 9, times 3 is 27. So all that work, quite a bit of work, but what you figure out is that this fraction reduces to 20/27ths. And now that we know what this fraction reduces to, we can, watching a football game, want to see if somebody scored, we can multiply that by this. We can say, all right, well, let's see, let's switch colors here. Maybe black I haven't used. We can see 23,760 over 32,076. We decided that was just 20/27ths. Maybe a better way to write that instead of 20/27ths is in this form. 2 times 2 times 5 divided by 3 times 3 times 3. That's what I got right here. And what I want to do is multiply that by 3/2. And what I can do is, rather than just multiply straight across, cancel out those 2's, cancel out those 3's. And what we're left with is a 10 up top and a 9 on the bottom. Alright, and then finally, this last guy here, now we want to add 3/2. What we'll do is again take advantage of the fact that that this fraction is just this right here. So I can say, switch to another color. This is really just 2 times 2 times 5 divided by 3 times 3 times 3. And to that I want to add 3/2. And I can't do it as it stands right now, but I could get a common denominator. To get a common denominator, what I'm going to do is I'm going to multiply this side by 2 over 2. Maybe I can write that in just in another color, 2 and 2. And I'm going to multiply this side by 3, 3, 3, 3, 3, 3. The reason I did that is now we have the same denominator on both sides. On the bottom here we have whatever 2 times 3 times 3 times 3 is. And up top, 2 times 2 times 2 times 5. 2 times 5 is 10. 2 times 2 is 4. 10 times 4 is 40. 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. So what we get is 40 plus 81 is 121. And 2 times 3 times 3 times 3 is 54. Whew. And we're almost done. We should double check to make sure this doesn't reduce. It turns out it doesn't reduce. 54 you can write as just 3's and 2's, and neither 3 nor 2 divides into this guy. So it turns out that this is our final answer. That last one was kind of hard. And that's the end of this perfect problem.